Okay, big picture episode 8, Randall.
Number 8?
Number 8. Last week was a bit of a caveat to our normal story. We're talking about your life and kind of what brought you to this point. But now we are back on the path of looking at what could have destroyed the world.
Well, it sort of did destroy the world, or at least parts of it, large parts of it, yeah. So, we were talking about the Missoula flood, right? We were talking about the so-called Missoula flood. I'm going to suggest that it gets renamed to the Cordilleran flood for reasons that will become apparent as we continue to talk about it. Only because I feel like the origins of the flood was not Lake Missoula, which is named after the town of Missoula and the basin of Missoula, which would have been one of the major basins that held the lake. We'll get into that, but we don't need to do that so much right now because I want to kind of cast the net. I want to start from where we left off and cast the net wider.
Right.
You know, we're about to embark next week on the Bonneville flood tour. We're going to follow the route of that flood from Salt Lake City north through Red Rock Pass, and then we're going to follow the Snake River Canyon, and we're going to actually follow the route of that flood. And as we go, we're going to be looking at the evidence that has been left behind in the landscape, mega-scale evidence. So we've already spent quite a bit of time talking about the Bonneville flood. Yeah. So just refer people back to that. If they haven't seen it, they can watch that or rewatch it. But we're going to go beyond that. We're going to get into the continent, the larger continent as a whole, the North American continent.
That's where we left off. I think it was episode 6, where you shared a map of all these different points across North America that had evidence of megafloods and cataclysmic damage.
Yes. Well, I'm going to read, now this is from maybe 15 years ago, but it's still, of course, up to date in the sense that what was being discovered and reported on for the last 25, 30 years is all pretty much mostly accepted, although I am questioning the ultimate origins of the flood. Okay, but so this is just some good basic information for people who want to understand the specifics more. So we have here, this was from the 2009 Portland Geological Society of America annual meeting. And at 2009, I had already been going for at least 11 or 12 years out exploring the floodlands of the Pacific Northwest. And of course, also by this time, I had gone and visited most of what we're about to look at in the larger view of the American continent. So anyways, they say here, this is what Victor Baker reports. He says, megafloods, which are terrestrial water flows with discharges exceeding 1 million cubic feet per second. So, 1 million cubic meters per second. So there's about roughly 35 cubic feet in a cubic meter.
Yeah.
So what that means is if you multiply 1 million times 35, you're going to get about 35 million, which is pretty much right in the ballpark of the Bonneville flood. Maybe a little more. We talked about between 35 and 40 million. So the Bonneville flood represents kind of the lowest stage volume of what is now defined as a mega flood. So say 35 million cubic feet per second, and then up to flows during the Missoula flood that were up to 300, 400, 500 million cubic feet per second. So in order, I'm a little hoarse today, which is an order of magnitude greater than the Bonneville flood. So you can see there, let's just in round numbers, 40 million, Bonneville, say 400 million.
From Missoula or Cordilleran flood.
Yeah, like the flow that might have cut Grand Coulee, for example. That's estimated at about 300 to 350 million. The discharge through Wallula Gap in about the same magnitude. The flow coming down the Spokane Valley northeast between Lake Pend Oreille in northern Idaho and Spokane, Washington, that reaching there, according to Baker's calculations way back in 1973, that haven't been disputed, are up to around 700 to 800 million cubic feet per second.
Oh my gosh.
Yeah, so that's like 20 times the volume of the Bonneville flood. So anyways, they're the largest known freshwater floods, with flows comparable in scale too, though of shorter duration than ocean currents. So you almost have to imagine oceans moving over the land to try to get a concept of the scale of the thing.
Thousands of feet deep and miles wide.
Yes, although, and I should actually probably go to presentation mode, although there are no modern examples of megafloods, thank God, because if there was a megaflood, such as what occurred at the end of the last ice age, any time within the last 5,000 years, it would be the most stupendous event that had happened in human history, far and away. Although there are no modern examples of megafloods, such flows occurred during major periods of glaciation. A prominent example is the paleo flooding caused by late Pleistocene outbursts from glacial Lake Missoula, which formed when the Purcell Trench of the Cordilleran ice sheet extended south from British Columbia to the basin of modern Pend d'Oreille Lake in northern Idaho. The ice thereby impounded the Clark Fork River drainage to the east, forming a lake extending into western Montana with a volume of about 2,500 cubic kilometers.
Oh my.
Which is about 600 something, 600 cubic miles, and a depth of 600 meters at the dam. So if I say 600 and a meter is 3.28 feet, that gives us just under 2,000. Although, since 2009, a number of traces of higher shorelines have been found. So it appears that the water at the region of the dam may have risen to a height of about 2,100, to a depth of about 2,100 feet, but only for a very short while. So it was like and of course, it has to be borne in mind that the water level was constantly fluctuating throughout the whole process. But it seems like that 4,250 feet above sea level was the highest that the water ever rose. It was only there for a short time, so it didn't create a really prominent shoreline or strand line, but it did leave enough to show that the water apparently did temporarily reach that height. And then it seemed to stabilize at about 4,200 feet above sea level throughout the entire basin.
So short time, meaning a day, a week, a month?
Less. Well, yeah, probably somewhere between a day, a few days, and a week or two, probably at the most. Because any longer than that, the shoreline would have been much more prominent than it is.
Okay. Quick comparison for just the scale of flood flows. Do you know what the highest amount of water flowing or flood flows there was during Hurricane Katrina or other modern flooding events?
See, that's a little different because, like with Katrina, you've got a storm surge.
Right.
And, it's going to be an extraordinary volume of water that's being pushed ashore by the high pressure storms. But what it's like right here, the largest Lake Missoula outbursts were in the range of 10 to 20 sverdrups. A sverdrup is the unit of measure used to measure ocean currents. So one sverdrup equals 1 million cubic meters per second. And a cubic meter, again, is about roughly 35 cubic feet. So you got about 35 million cubic feet per second. That's one sverdrup. So the Bonneville flood essentially is roughly the same size as the standard unit of measure for measuring ocean currents, if that's helpful at all. Now, if you've got a volume 10 times that, like 350 to 400, now 350, that's the flow out through Alula Gap. That is the estimated flow for Grand Coulee at its peak, Moses Coulee at its peak. And now, how does that compare? It's difficult to say because, clearly like a tsunami coming ashore is a very short-lived event. And I don't know if I've ever seen anybody trying to calculate the total volume of a tsunami? I mean, I imagine you could, and it's probably been done. Maybe if you were to look at chevrons and get an area and then figure out a depth. I know that the Madagascar chevrons, the depth was in excess of 600 feet.
Yeah, we looked at that. I think we looked at that the first or second
We did,
episode of this, yeah.
Right. So I would imagine you could come up with some idea of the total volume of a great tsunami
See
event
if
like that.
AI has some type of answer for us.
You think AI is?
I don't know. We'll see, but we'll let it search, do some research here.
Okay. So the Missoula floods were responsible for generating the channel scabland of east central Washington state, a complex of anastomosing rock-cut fluvial channels. What do we mean by anastomosing?
I'm not sure.
Okay, so anastomosing simply means branched. You have like a main channel that separates into multiple channels. Then those multiple channels may converge back into single channels. So it's a branching pattern of streamfall. If you look up anabranching, it'll tell you, anastomosing.
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 So there's an example of anastomosing, a branching stream pattern, anastomosing rivers, a review of their classification, origin, and sedimentary.
Oh, here's a good one.
Yeah, there you go. That's a perfect example of anastomosing. So, the channel scabland of eastern Washington is a complex of anastomosing rock-cut fluvial channels. Fluvial means flowing water. These flows deeply inundated the Columbia Gorge and the Willamette Valley before discharging into the Pacific Ocean. Other late glacial megafloods occurred along the margins of the great ice sheets, and this is what we're going to be looking into now. Other late glacial megafloods occurred along the margins of the great ice sheets that formed during the Pleistocene in North America, Eurasia, and South America. River basins connected to these ice sheets were impacted by the flooding such that invasions of water changed drainage patterns, enlarged valleys, and delivered huge fluxes of water and sediment to the oceans. Numerous spillways were flood integrated into temporary rivers in parts of North America, such as the St. Lawrence, the Mackenzie, the Yukon, the Mississippi, and Columbia rivers, and in Eurasia, and I won't necessarily, the Dnieper, Volga, Yenisei, the Irtysh, the Ob, and others. The late Pleistocene megafloods are associated with a broad range of hydrologic and climatic changes that are only now being fully understood. And I would say being understood, but not yet fully understood. Okay. All right, so here's North America, and there was the situation at the end of the last ice age. Of course, this is not truly accurate because this is showing the current coastlines of North America, which would not have been the case when you had all this ice piled up. Coastlines would have been far seaward. Mm-hmm. But this is the is the graphic you were talking about.
Exactly.
These all represent great flows of water. And yeah, this is not even comprehensive, but we did go over this, so we won't spend a lot of time looking at it.
Yeah,
let's see. So I've investigated the Valles Calderas overflow, the Silver Lake, Soda Lake, Manly flows, the Bonneville, the Missoula, the Athabasca, the Livingstone Lake. I've not gotten up here to do the Lake Agassiz superflood or the Mackenzie River floods, but the Superior floods, the Ontario mega floods, Lake Wisconsin, all of the others I've personally investigated in the field.
And how long has it been since you started investigating in the field?
Oh, in the 90s. The 90s. I spent 20 years studying it, and then finally in the 90s, I started getting the resources and the time that I could actually do what I'd been hoping to do long before, which was get out in the field to personally investigate and learn directly from, a direct observation. So we have explored the regions affected by the two greatest acknowledged floods in the history of North America, the Great Missoula and the Great Bonneville. Now, the key word here is acknowledged. Now, this was written probably 10 years ago. Now, I think we have enough proof that we can say, yes, there have actually been floods with flows greater than the Bonneville, okay, some of which are listed right here. For peak discharge and raw stream power, these events are not likely to be surpassed. However, the effects of megascale catastrophic floods are by no means limited to the region directly affected by these two floods. It will be the purpose of this episode of the saga to elucidate the myriad effects of colossal floods on a variety of landscapes around the remainder of the North American continent, and to demonstrate the probability that the Missoula and Bonneville floods were actually a limited regional manifestation of a much larger event. So, we'll just get right into it. I think most people know the Pleistocene epoch of the Quaternary. These two together is the Quaternary. Comes after the Pliocene, characterized by the appearance and reoccurrence of ice ages after the relatively mild Pliocene. The epoch in which human beings emerged, the Pleistocene, began about 2 million years ago and ended about 10,000. Now, since I did this, put this together, again, like I said, probably 10, 12 years ago anyway, this number here is now more like 2.6 million. And this one has now been pretty precisely refined to 11,600 years ago. In fact, you know what I'm going to do? I'm just going to do this.
In real time.
In real time, I'm updating my show here. We'll go
How long was the Pliocene epoch?
Oh, let's see. The Pliocene was went back to 5-point-something million years. So it was over 3 million years.
Wow. So previous to the Pliocene, was there a more volatile climate with ice ages?
Yes, there have been, but not immediately before.
Okay. What kind of marks the divide between these epochs?
Well, okay, that's been an evolving process. Used to be, it was looking for an area where nothing had happened. So what that means is, let's say you've got, a million years, and something happens to start it and something happens to end it. But in order to define it, what they were looking for originally was some horizon where nothing happened, and say, okay, this is the Pliocene, this is the Eocene, this is the Oligocene, right? Well, what's changing now is that the horizons are more and more being used as the lines of demarcation. And these are where something did happen. Like at 11,600 years ago, something did happen.
Yeah.
There was a major melting event. It was associated with, I think, the final collapse of the megafauna ecosystem. It also was associated with a rapid pulse of sea level rise. It was also associated with a spasm of really fast warming that jerked the planet out of the ice age. There was a bunch of stuff that sort of collected around that 11,600 year ago date, right? So now that is an event horizon, the upper Younger Dryas boundary. The lower Younger Dryas boundary is an event horizon. We can go in and we can see now more and more, I think you could say the trend is getting to defining the epochs according to when did something happen, rather than let's define the epoch as much as we can in the middle where nothing was happening. See?
I see, yeah.
Does that make sense?
Yeah, so it's essentially marked around where there's been large events that changed the climate at drastic rate.
Yes. Okay.
Ooh, some more flood French for us.
Yeah. Alluvial, pertaining to or composed of alluvium, which simply means deposited by a stream or running water. Alluvium is the general term for detrital deposits made by streams on riverbeds, floodplains, and alluvial fans, especially a deposit of silt or silty clay laid down during the time of the flood. So if I say now, when we looked at the big rock, remember the Okotoks?
Yes.
When I say now that that was had depressed, had sunk into the alluvium, you know what I'm talking
Yes.
about. And that area of the prairie there, you dig down through the layer of sod, vegetation, and it's alluvium. How thick it is, I'm not sure. It probably varies throughout the pathway, but it is alluvium. And then an alluvial fan, people can look at this for themselves. Colluvium.
And you can tell it is alluvium because of some type of mineral content in the silt or in the silty clay. How do people figure out that it's alluvium versus, I guess, just geological?
Well, for one thing, I'll show you the difference. For one thing, alluvium is deposited by water. So water tends to cause structure. For example, glacial, like till, has no structure. I'll be showing you a picture of some till coming up in a minute here. Usually there's bedding, there's foresets perhaps in it. There's some type of a structure that's quite easily identifiable as water deposit.
So it's structural rather than chemical.
Yes, I think it would be structural rather than chemical because, it could be from what you would call a terrigenous deposit, meaning it comes from land. It could be a marine deposit from a storm surge or a tsunami. It's just material that has been deposited by water. And it could be any range of compositions. So it's less, but obviously if you're going to be looking at a storm surge, you're going to find marine fossils within that deposit, which will tell you immediately. Likewise, there are freshwater fossils that are in lakes and rivers that could end up in the alluvium.
Mm-hmm.
It may be barren of fossils, just depend. If you've got a flash flood going across a desert floor that's had no marine life on it at all, you're probably not going to find a lot of fossils in it. But again, what you're going to be looking for is structure.
Mm-hmm.
The water does a very different thing than just random chaotic. But when we get down here, look at this. So you got colluvium is a general term applied to loose and incoherent deposits, usually at the foot of a slope or cliff and brought there chiefly by gravity. Talus and cliff debris are included in such deposits. So again, colluvium would be a deposit, and it's gravity emplaced, not water emplaced. And again, if you've got a landslide or a cliff collapses and it all falls down, the resulting material is just going to be chaotic. You're not going to go in there and expect to see any kind of current structure.
Yeah.
That's been
any type of coherent pattern. Would colluvium include windstorms or something like that?
No.
No. Okay. So just by gravity. Got it.
Yeah. Now, could you have wind? Yeah, perhaps, but mainly wind deposits can be an aeolian deposit.
I got it.
An aeolian deposit. And it's actually, you can distinguish a wind deposit from a water deposit. Once you've looked at a few, like out southwest, there's lots of really great sandstone outcrops that are wind deposited. In fact, put in there in your search engine there, let's see, sandstone aeolian is spelled Aeolian. Sandstone aeolian deposits. Should you?
Yeah.
Oh yeah, that one on the right there, the large one, that's a beautiful example. And you start looking at photos, videos, actual outcrops in the field. After you've looked at aeolian deposits and fluvial deposits, you'll begin to detect the differences. So they're kind of subtle maybe at the beginning because, obviously moving air and moving water, they're both fluids.
So I can't type for anything.
Let's see where. There's a braided.
Yeah, that's just showing the.
That's a good one to pause on, though, right there. Look at the terms.
Terminal
You're
moraine.
going to learn a lot of new terms here, Beckett. End glacial, that means within the glacier. So you might have, see, end glacial sediments. That's sediments that are being moved inside the glacier mass. Then you look up there, you see lateral or medial moraine. Supraglacial sediments, that's riding on top of the glacier. And then finally, you've got at the bottom, you've got subglacial till. So that's at the bottom of the glacier.
Yeah.
And then you've got at the snout there, you've got the outwash sediments. So that meltwater coming from under the glacier is moving usually fairly fine-grained material, forming the outwash. Like you can go in Indiana, and we'll look at this on the LiDAR maps in a minute. We can look at that. If you look at places like Indiana, you'll see the terminal moraine where the glaciers came to and built these very hummocky deposits of hills. And then just south of there, it's flat because that's all the outwash. The outwash is the fine-grained stuff that is discharged from beneath the glacier, and it pretty much spreads out and creates a very flat landscape. We'll see that in a minute. And then finally, you see down here where it says terminal moraine.
Yeah.
Okay, so what this tells you is that this glacier here has receded a bit, because at one point its snout was right down there at the terminal moraine.
Okay, and it just melted, and that's the.
Yeah, and it's receded back because it's been melting, and that melting has created the outwash sediments.
Uh-huh.
And then now let's look at the term drift. Now that's kind of an archaic term because what drift is, it's like it says, it's a general term for all rock material transported by glaciers and deposited directly from the ice or through the agency of meltwater. It is generally applied to Pleistocene deposits in large regions that no longer contain glaciers. Term originated in the 19th century. But the key is they're looking at it. You could look at glacial deposits, you're going to see in a minute, completely chaotic with no observable structure. Fluvial deposits, you're going to see structure. You're going to see bedding. You're going to see layered sedimentary deposits, etc. Glacial fluvial, which is the modern term for drift. The drift was the 19th century term for this stuff that looked like it was a combination because it was very chaotic, yet there was still some structure in it, which you do not find that structure in direct glacial deposits. Okay, so then the next term is till, which is unstratified drift. Unstratified, again, no evidence of water deposition. Deposited directly by a glacier without reworking by meltwater and consisting of a mixture of clay, silt, sand, gravel, and boulders ranging widely in size and shape. And then the final term, which you saw in the graphic you pulled up, end glacial, is contained, embedded, or carried within the body of a glacier or ice sheet, said of meltwater streams, till, drift, moraine, etc. Now, here's a nice little breakdown. Let's go here. So generally, you've got two ends of the continuum, the processes. You've got erosional, and then you've got depositional. If something is being deposited, it had to have been eroded from somewhere first, right? So if we look down erosional, we have the scabland, which is butte and basin topography. I think we saw pictures of that. Shear-walled canyons and gorges. Slow erosion tends to make V-shaped valleys. Catastrophic erosion tends to leave shear walls, vertical walls. Coulees and spillways. Well, coulees are large channels that have insignificant to no water flow within them. And the genesis of the coulee is clearly on an operational scale way, way beyond whatever is present there in terms of water erosion. Like Grand Coulee has no flowing water in it. Moses Coulee has a tiny little insignificant stream that had nothing whatsoever to do with the carving of Moses Coulee. Okay. Spillways, well, this is where, you understand that every river or creek has its own catchment basin, right? Mm-hmm. So like right here where we're at, if we go up to the end of the street up here, East College, that's actually the watershed divide between the Savannah River catchment basin and the Chattahoochee River basin. So if you were to go up there and you were to start dumping water in the middle of College Avenue, and some flowed to the south and some flowed to the north, what's flowing this way is going to end up going out to the Atlantic. What flows to the north is going to end up going into the Gulf of Mexico. So that's a watershed divide, right?
Yeah.
Oftentimes, county boundaries, state boundaries, and so on are associated with watershed divides, okay? Which could be either the topographic high or the topographic low. For example, a river or a creek is a natural place to have a political divide, right? You own that side of the water, we own this side. This is our state, that's your state over there. But also, for example, if you've got a high area where the water's shedding off in two different catchment basins, that's also a logical place, because you could say, okay, we've got this town here, and if you dump pollution into your watershed, it's not going to flow into ours because it's flowing the other way. It's flowing to a different river. I mean, it's a logical place to divide, municipal boundary, county boundaries, whatever the case may be. A spillway is going to be a channel that links two different basins or two different watershed divides, two different catchment basins. So let's say you've got a basin here with a rim around it, and then you've got a separate basin over here that's actually a different watershed. And the rain falling here this leads to one river, the headwaters of one river, this leads to a different. But then you get an influx of water from whatever source. It could be intense rainfall, it could be a melting glacier, whatever. This rises up, and it rises above the high elevation that forms the divide. Now it spills over. Yeah. And that spillover will oftentimes then erode and cut a new channel. And that's what we would think of as a spillway.
Got it.
Right? Now, you also got spillways because when you had melting, it looks like you had multiple melting regimes that affected the adjacent or contiguous landscapes in different ways. So if you've got supraglacial flow, let's say that you go 500 miles north of the margin of the ice sheet. Like, let's say, for example, we're looking at the Cordilleran, and we conclude that, well, it looks like a lot of this water flow originated up near the Chaco Plateau, up by
Prince George.
Prince George, yes. I almost was saying up by George Howard.
Way up north there.
Way up north. Prince George, but maybe we should start referring to
Prince George Howard.
Yes, I think we should, actually, when we introduce him at the everybody's give a big round of applause for
Prince George Howard.
Sorry. But if you go up there, you make the assumption that water flow originated there. Okay, so now you're talking about melting, obviously, because in order to have water flowing, you have to melt the ice. But so let's assume you've got melting, an epicenter of melting. A couple of things are going to happen. One, you're going to have water volume that's going to be able to, by one means or another, get through the ice to the bottom. That's going to become a subglacial flow. Other melting would be over the surface. That's going to be end glacial. Now, obviously, if you think about it, there's going to be a lot greater frictional resistance to the subglacial flow than the surface flow.
Yeah.
You just got this free flow in the air. So if it starts flowing, it's going to get to the margin first. Then, subsequently, the subglacial flows will reach the margin. This is important, I think, when studying the deposits around Flathead Lake. I think we can identify where supraglacial deposits came in discharging off the surface of the ice sheet and distinguish those from subglacial deposits that came afterwards, after the surface flows had already created a substantial volume of water. Anyways, let's go on with this. So we've got strand lines and shorelines. Strand lines is the term for the fossil shoreline. Dry cataracts. These are the recessional cataracts we've talked about frequently, that the sheer power of the streams flowing over the precipice pluck and quarry the material off the cliff face, causing the cataract to recede. Yeah. And that's basically what we have happening up at Niagara Falls. But this is at obviously a much slower pace than what would have occurred during some of these megafloods. Then we have buttes, pinnacles, and pedestals. Now, buttes, I should actually also suggest mesas. I should have put that in there. In fact, I think I will add that right now. Buttes. All right, good. So a mesa is essentially like a table, and it's a and again we'll look at if you pull up say Steamboat Rock. Now, Steamboat Rock is generally not defined as a mesa, such as you would find in the Southwest, and yet when you look at the scale of it, it is very mesa-like. It's wider than it is high. Okay, a mesa is an erosional outcrop that is wider than it is high. Are you finding anything?
Yeah. Okay, so we're looking at Steamboat Rock here.
Which is an example of what could be defined as a mesa. Now, yeah, when you scroll in, notice the cliff in the background. That cliff is also 800 feet high.
Yeah.
And prior to the flood, that was a continuous, that void of 800 feet removal of bedrock had not happened. The floods that came through there stripped away 800 feet of rock. And behind the photograph there's another cliff, right? So you have two pairs of cliffs, and then standing out midstream, you've got this 800-foot high called Steamboat Rock, because from the air, it kind of has the profile of a boat or a ship, which is immediately an indication that water was the agency of erosion here. See, so that would be a mesa. Now, typically, this is not ever referred to as a mesa, and yet, if you go to the southwestern deserts, you can find mesas, for example, down there in Monument Valley, that are basically the same height and the same width and the same length as this outcrop right here. But no one really suggests that they were the product of water erosion. In fact, the origin of these is usually just pretty much glossed over and assumed like somehow wind or whatever, but we're going to get to that. That's why we get through the whole continent here. So we've got these terms here: mesas, buttes, pinnacles, and pedestals. A butte is about as wide as it is tall, okay? A pinnacle is taller than it is wide, and a pedestal is a tall pinnacle rock with a sort of a extended, a cantilevered platform on top.
Okay.
And again, we'll see examples. Okay, then potholes is another erosional form. When you have extremely fast-moving turbulent water, you get this vortex phenomena, and that can literally drill holes in the bedrock. Now, that's erosional stuff. Now, like a depositional. Well, large gravel beds and bars, right? Boulder streams and block fields. I'll show you some examples of those. Large erratic boulders, alluvial and debris fans. So you got a gush of water coming through a mountain valley, and then it opens up, discharges into a basin. Perfect example is put in Mormon Point, Death Valley. And there's a beautiful example of an alluvial fan, if you see it from the air.
Let's look. Boom.
Let's see, there's probably
a better picture.
Well, actually, I've got some pictures here that I
don't know why it has that.
That's okay, because I've got pictures that if we get through this, we'll see it.
Yeah.
Okay, so you've got fossil lake beds.
Is that like John Reeves' Boneyard lake bed in Alaska?
Is which one like that?
Fossil lake beds.
No, a fossil lake bed is simply a dry basin that once held a lake.
Oh, okay. So it's a fossil.
Now, of course, it can have fossils in it.
Yeah.
And oftentimes does. But it just means that it's an extinct lake.
Makes sense.
And you had large examples of that, particularly in the southwestern deserts, of very large lakes. Manly Lake in Death. You ever been through Death Valley?
I have not.
Okay, so we're going to have to organize some tours.
Get boots on the ground, man.
Get boots on the ground. Manly Lake was a body of water that filled up Death Valley. What I believe is probably the driest place in North America. Once held nearly 1,000 feet of water.
Wow.
Yeah. Okay, so another depositional, and this is a little bit giant current ripples. Giant current ripples really are more accurately kind of a combination of erosion and deposition. But generally, I think they're more depositional than erosional. And they're usually, I think, built at the final, the waning stages of the flood. And then imbrication. Do you remember what that is?
I don't.
Well, we'll see slides, imbrication. You can look it up on
Oh, yeah.
Yeah. So we've got imbrication. We'll show examples. Then down here, I've got things that are definitely combinations of erosion and depositional. It's hard to draw a line where erosion stopped and deposition started. So that includes drumlins, eskers, tunnel valleys, terraces, and benches.
Yeah.
Okay. I don't know if this is all encompassing everything. I'll add to this if there's more that comes up. But this is, gives you a good working basis for, understanding and developing the vocabulary to talk sensibly about this kind of phenomena, right? Because, clearly, if you're talking about, imbrication, if you know what it is, then instantly understand the implications of imbrication.
Right.
Okay, let's go on here.
And we'll look at examples of that.
Yes, we will. This is a rather interesting map because it shows a couple of things. The maximum extent of Wisconsin glaciation. You follow this around, and you see the hash marks defining the margins of the ice sheet. And you'll see that all of the modern Great Lakes are all not existent. They are under the ice sheet, right? But look, put all of the Great Lakes together, and you still don't have the volume of Lake Agassiz. This was a massive, massive body of glacial meltwater. Freshwater, not saltwater, not marine. Freshwater. When we were taking Graham across from Portland to Minneapolis, one of the last two places we stopped are actually indicated by the arrows that you see here. This was the southern outlet of Glacial Lake Agassiz.
Mm-hmm.
And that's what formed the Minnesota River that I've told the story about so many times. Glacial River Wine.
Yeah.
That was 4,000 times greater than the modern Minnesota. And when I first beheld that large valley of the Minnesota, I had this impression. Okay, so that was this discharge point, the southernmost discharge point of Lake Agassiz. There was other discharge points. You can see Lake Agassiz here is connected with Superior. And then all of the Great Lakes are interlinked, and you can see that they're discharging over here. Here's a major discharge going up the St. Lawrence Seaway out to the ocean. So this was going over, feeding into the Mississippi, which then flowed to the Gulf of Mexico. Right in here is where the St. Croix Wild and Scenic River forms the northern border of Minnesota and Wisconsin. And you can see that the Lake Superior lobe discharged down that pathway, and that's where these giant potholes are that was the last place I took Graham. That was the last spot we visited on his 2-week tour when he was researching the megafloods. So this is a kind of a useful map.
Yeah.
And you can see here this glacial lake Agassiz is interconnected with all of these other lakes up here that ultimately are discharging north into the Arctic Ocean via what is now the Mackenzie River. And the Mackenzie River occupies a massive, oversized valley with scabland features throughout it.
So I may have missed this, but is Glacial Lake Agassiz a subglacial lake? Is it formed from the melting of the glaciers?
It's formed directly from the melting of the glaciers. The question is the timing of that transition from glacial ice to massive amounts of meltwater. Not only its timing in the larger temporal framework, but its timing also, how long did it take that volume of ice to melt and form the volume of water that formed Glacial Lake Agassiz? Personally, I think it was a lot quicker than the standard models of deglaciation and melting allow for. I think it was a lot quicker. And that's something we'll be talking about down the road.
Okay.
But look, you can see, like right up here, you can see flow paths this way. Then you'll see a flow path down here, flow paths over here. These are showing directions of flow, meltwater flow, because all of it, of course, is headed back to the oceans. So colossal four-set gravel deposits. Now, four sets, you see the tilt? Okay, so, and you can see here that the variation in the color shows different mineral composition, different content. I've not looked at the provenance of this. Remember the term provenance? Provenance?
Yeah.
We have lithology that tells you what kind of stone, and then the provenance tells you where it came from, basically. Where did it originate? So it says this is evidence for giant flood flows from the melting Cordilleran ice sheet. The glacial fluvial flooding did not contribute to the formation of the channel scabland of eastern Washington. Instead, it discharged into the Strait of Georgia at Vancouver, BC. So this was gigantic meltwater flows that were flowing down the Fraser River, and they're just within the last few years some new studies coming out confirming what I knew in 1999 when Brad and I traveled down long reaches of the Fraser River, ultimately to its discharge point. You know, the city of Vancouver is built upon the massive debris fan that splayed out from the mouth of the Fraser River Valley. So we followed that and photographed all the way down evidence of gigantic floods. That was 1999. Then in 2021, a team of geologists published a paper saying that there were catastrophic flows down the Fraser River. And then that was followed up by a second study. I think it just came out this year. Again, confirming more evidence that confirms mega floods down the Fraser River. Because the reason I did is because we went up to the headwaters of the Fraser up near Prince George and the headwaters of the Columbia. See, this here is the headwaters of the Columbia. No, wait a minute. No, this is I'm sorry, this is the Fraser.
Yeah, that's the Fraser.
And then we've done
Big
this,
rocks,
we covered this, so we're not going to get into that. But here you can see, again, now when I say this rock was deposited and it was iceberg rafted, so you're talking about an iceberg here big enough, essentially the size of a tanker ship. It's floating an 18,000-ton rock, hauls it hundreds of miles from its place of origin, and then sets it gently down on the prairie into unconsolidated alluvium. And you can see how the rock sank under its own weight. And as it sank, you can see it had a crack in it. It sank, and look what happened. See?
Yeah, it split.
The crack opened up. Now, there's no way that if that was transported end-glacially or subglacially, there's no way it would have survived intact.
Yeah.
But it was, even, you can see here that there's a fracture line here, there's a fracture line here. You can see that the corners are acute angles, sharp angles. They didn't get ground off. This had to have been transported via iceberg, sitting on top of an iceberg. And that iceberg is being swept along in a gigantic flood. When the floodwaters finally relax, the iceberg comes to ground, and then the launching of this process would have been catastrophic almost beyond imagination, because you've got to simultaneously rip gigantic boulders off the shoulders of these mountains, megaload them onto the ice sheet while the ice sheet is being fractured into a million icebergs, and melt the water that's now going to float those icebergs. All of that's happening simultaneous virtually.
Wow.
The end process is this great rushing flood is sweeping along, in this case to the south. Iceberg comes to ground, flood finally drains off. Now that iceberg, huge iceberg, probably is going to take years to melt away. So the final stage of this process is the iceberg's melting. As it's melting away, this big cargo, this giant rock, is just slowly sinking down. And then it sits onto the landscape, which is basically soft because it's saturated with water, right? So now it sinks. And then gradually the mud layers dry, and now it transforms into the modern prairie.
And this is an 18,000 ton rock?
That's an 18,000 ton rock if you take it all together. And then south of here, when you follow this train to its end, where it transforms into the headwaters of the Missouri River, right at the Montana border, that's where you see the giant ripples. And these ripples, that right there, that white line is a mile long. So these are huge, huge ripples. And mute testimony as to the magnitude of this water flow. Now, this is completely east of the Continental Divide, all of this that we're seeing here. Channel Scablands, Missoula, Lake Missoula, all of that is to the west of the Continental Divide. So you've got big flows coming off to the east, other gigantic flows coming off to the west.
I see, yeah.
Yes. Now, one of the questions in my mind is that I want to know, what is the exact timing of those two events? Did they precede? Did one precede the other? Or I would be inclined to think that they're happening simultaneously. Here you see the ripple. This is the Montana line right here. Montana-Alberta line. This is Milk River.
Yeah.
So now let's come to the east. Glacial Lake spillway incision and deposition of a coarse-grained fan near, I don't know how to pronounce this, Watrous, Saskatchewan. Watrous, yeah. So this appeared in 1994 in the Canadian Journal of Earth Sciences. The legacy of catastrophic drainages of proglacial lakes is a characteristic suite of erosional and depositional features. Spillways generally lack deposits from the floods themselves because of the intense erosion that accompanied lake drainage. So again, think back to our model we're talking about. Here's a basin separated by a drainage divide. Water rises up, spills over, starts down-cutting, but what it's doing in the process is flushing everything out. So if you go to the other basin, the downstream lake basin, there you will find the deposits, either forming the floor of the fossil lake, or there will be a debris fan spewing out from the mouth of the spillway. But you'll be able to distinctly discern that. And you'll be able to tell from that which way the water was flowing. Because on the upstream basin where it's flowing over, there's not going to be a depositional alluvial fan. That'll be on the downstream side, right? Now, one way really to help understand these processes is if you just spend time. Now, I get an opportunity because, building, we'll always have cleared building sites. So you go in and you clear a building site. Now you've got clay or sand or silt matrix. You have a heavy rainfall. You come back the next day, and there it is, a whole channel scabland landscape laid out in miniature. And you can see everything.
We were looking at that the other day.
Yeah. What we were looking at, there wasn't really a good example. When you see a good example, it's unambiguous. It's unmistakable, right? You'll have recessional cataracts. You'll have meanders. You'll have debris fans. You'll have all of it. Well, you may not have glacier. You won't have drumlins.
Yeah.
Drumlins are unique. You have to have a subglacial flow and over a thick cap of glacial ice, because what happens is normally water flowing free surface over the ground will seek its own level. It can't do that under a glacier, can it? Now, obviously, that flowing water will melt, will raise the roof of the channel. It absolutely will. But it's still under pressure, and it's that pressure that then takes and shapes the till, the chaotic till, into these long alluvial forms. The size and morphology of these channels are the best indication of magnitude and duration of these events. The morphology of the Watrous Spillway is similar to many proglacial lake spillways in the mid-continent prairies of Canada and the United States. These channels were rapidly incised by erosive flows of high discharge. Despite the problems in quantifying the characteristics of glacial lake outbursts, the channels and deposits themselves provide confirmation of the impressive magnitude of these events. Now, there are dozens and dozens of these huge spillways, right? All the way from the headwaters of the Missouri there by the Milk River ripples, you come east, all the way over to the Great Lakes, you find dozens and dozens of these massive spillways, right? Most people have no clue. But here's a difference. Those spillways that are mid-continent, they're traveling 1,000, 1,200 miles to get to the ocean. The channel scablands are traveling 200, 300 miles. They're also starting from an elevation 4,000 feet above sea level. So what's happening? You've got much steeper, like this. Steeper means faster velocity. Faster velocity is more shear power, more stream power. More stream power means far more erosion and moving of material, all of that. The slower, lower gradient in the mid-continental region, it's not as erosive. However, the volumes of water, way up there in the millions of cubic feet per second. Mm-hmm. It's just that they're moving over a much slower, lower gradient, so they're not as erosive.
Makes sense, yeah.
Well, it does make sense. Glacial lake outbursts occurred in the northern Great Plains as ice marginal lakes suddenly drained, forming an interconnected system of glacial lake spillways. The outbursts were highly erosive. So an interconnected system of glacial lake spillways. So they're not just going in isolation. They're actually forming this whole network that we're really beginning to see now with LIDAR. That is kind of laying, under the topsoil, under the glacial debris that was put down. I mean, again, an important point to emphasize here is that it's only within the last few decades that we've really gotten to this pinnacle of technology where we can begin to see this stuff. I mean, it took J. Harlan Brett's 25 years of laborious traveling over the area of the channel scablands to make a remarkably accurate map. But that map now you can see instantly on Google Earth.
And so, yeah.
Can you imagine if Brett's in the 1920s or 1930s had a tool like Google Earth to help him in his exploration?
The world would be different. We'd have a way different understanding.
Oh, totally. But see, we're there now. And so we have these tools. And what these tools are revealing to us is mind-boggling. It's amazing. And it really throws into bold relief some of the assumptions and misassumptions about what may or may not have happened in our own human past on this planet.
Yeah.
And of course, once you realize that these megafloods, these diluvial events, are worldwide, then you can begin to appreciate why so many cultures have legends of gigantic, cataclysmic, world-destroying floods. Because the fact is that a flow of 500 million cubic feet per second is going to be world-destroying.
Yeah.
Not planet-destroying in the sense of a supernatural flood drowning all the highest mountains on Earth. But as far as any survivors of an event like that,
there's very little.
There's going to be very few survivors. There's going to be some, because obviously here we are, right? But to a lot of the survivors, everything that they knew as their world is gone. It's gone. It's erased from reality. It's erased from creation itself. And so in that perspective, you wouldn't necessarily even know if somebody 300 miles away had survived. Well, you have no way of communicating with anyone outside your own group that has survived. Travel? Well, travel is going to be very difficult because how do you travel across 200 or 300 miles of utterly devastated landscape? No food to forage, nothing to hunt. It's just a total wasteland. Now, give it a few centuries, what's miraculous is how nature quickly can begin to restore a devastated wasteland in the aftermath of a catastrophe like that. A great laboratory to watch that unfold over decades is Mount St. Helens. I made one visit there. I'd like to make several more to see what has changed just in the last, 7, 8, 10 years ago that I was there. But yeah, there is a place where you had a couple of hundred square miles that were just rendered completely barren, like the moon. And now you see, by degrees, nature is recovering and restoring, right? You also see some very interesting alluvial or fluvial stuff going on because now you've got these layers, thick layers of volcanic ash, right? Well, now you have a rainstorm. The rain is creating a whole new set of incisions, of anastomosing channels. You can see all of this stuff kind of on a median scale, right? Because some of those gullies now cut into the volcanic ash are 200 feet high, right? But you go in there, and again, everything that you see, that really impresses the scale and variant nature of water erosion and deposition.
Do geologists just not see this because they don't want to look this big? It seems like you can see examples of this at much smaller scale, so it's not like we don't understand the phenomena, but are we just not looking large enough, or is geologists?
That's what I think. Academia? I don't think we're looking large enough. See, this is the next stage, and it's starting to happen. Like these guys here, Mark Lordell and Kehoe, this was in 1987. Notice if you read their work, they're not in any way connecting it with, for example, the Bonneville flood or the Missoula flood. They're looking at it kind of in its own compartment. Well, you had these big glacial meltwater spillways. Well, but then I think now, can we integrate those spillways, and are clearly evidence of catastrophic melting? If one of these, excuse me, if one of these was considered catastrophic, then what are we talking about when we're talking about dozens and dozens of them flowing simultaneously? What does that imply about the melting and the rate of melting to the Great Laurentide ice sheet to the north? So now we see what kind of things would we look for out in the field. Here you have a giant boulder bar. This thing is probably hundreds of feet, maybe a mile long, and it's composed of probably a few million boulders, and you can see they're all rounded. And they've been ripped from somewhere, but they've been transported far enough that
tumbled around,
yeah. Then when the water drained away, it left this as its calling card. Okay, so this is Drumlin's. Now look at this carefully. Which way was the water flow? Can you tell?
The tail is
downstream.
Downstream.
The blunt end is upstream. So this was a flow from lower left to upper right.
Okay. Oh, okay. I see.
Yeah. Yeah, like, look right here. You see this is blunt right here? And then you can see, this one isn't quite as clear, but yeah. All of this this is a flow up to the right. There you go. Flow direction. There's another Google Earth view of the Drumlin swarm. And that's a nice one because it gives you the sense of what a Drumlin kind of almost looks like. And see, here's the thing. When you're traveling over this landscape, like I have several times, you're up in the middle of a Drumlin swarm where there's thousands of Drumlins, but you don't know it because everything is covered in trees, right?
Yeah.
However, now with LiDAR, it sees through the trees, and you can see what's under the trees, see? So it's starting to, the planet is revealing itself to us. Excellent example of a braided or anastomosing stream pattern. This is the Muddy River in Alaska above its junction with the McKinley River. Note the small size of the modern water flow compared to the massive sediment load. So basically what you had here was a gigantic meltwater flood that dumped huge amounts of sediment.
Yeah.
And then now the modern river is just, meandering casually back and forth over this. But the old assumption is that all of this sediment would have been deposited, slowly over long periods of time. And it was probably one or a few major depositional events that left that behind. And undoubtedly, I think it would have been meltwater, glacial meltwater flows. Let's just keep going here. Important work, John Shaw, right? Bruce Rains, late Wisconsin subglacial megaflood paths in Alberta. Subglacial sheet floods were proposed on the basis of the landform evidence of the Livingstone Lake Drumlin field in northern Saskatchewan. Such floods require the release of enormous volumes of stored water, and it is important to demonstrate that such storage and subsequent catastrophic releases are feasible. Some Laurentide subglacial sheet floods were at least several hundred kilometers wide and tens of meters deep. So try to imagine several hundred kilometers wide. Well, you could be talking about 100 to 150 miles wide and tens of meters deep. That could be 100 meters deep. So think of, a subglacial river. So mean velocities at maximum discharge are estimated to have been at least 5 meters per second. Instantaneous discharges in excess of 10 to the 6th cubic meters. So that's 1 million cubic meters per second. So that's your Skerdrup.
Yep.
That's your unit of measure. So in excess, instantaneous discharges in excess, total flow volume of 8.4 times 10 to the 4th cubic kilometers. What that is that's, well, what's 8.4 times 10 to the 4th? Well, I can pick up my calculator right here, and I can go 10 up to 4 equals times 8.4. And what I get is 84,000 cubic kilometers. And there's roughly 5 cubic miles per, reverse that. A cubic mile contains, I think, around 5 cubic kilometers. So if I divide this by 5, we're looking at about 16,800 cubic miles. Now that divided by 600, the volume of Lake Missoula, so that's like on the order of 30 Lake Missoula discharging under the ice sheet.
Oh my.
And mainstream geologists couldn't handle it. And they made what I think is a valid criticism. And I think the weakness in this theory, which is right here, it says, right here at the key, storage and subsequent catastrophic release. So the critics said, well, how the hell do you store that much water? How do you store, 28 times the volume of Lake Missoula? And John Shaw, who came up with this idea by looking at the Drumlin, studying them and seeing, to me now, having visited 3 or 4 different Drumlin fields, seen with like one of John Shaw's leading graduate students, Jerome Lessman, I'm totally convinced, yes, they were created by subglacial floods. The weak point, though, again, and this is where the critics have savaged John Shaw's theory, is, well, how do you store that much water? Can you store that much water subglacially? Well, no, that doesn't make any sense, does it? I mean, how do you store under the ice 30 times the volume of Lake Missoula? Right? Do you store it on top? Well, no, we know that that's impossible because every season you get lakes forming, meltwater lakes forming in the summer that quickly drain away through cracks in the ice sheet. And they flow to the bottom of the ice sheet and they come out and discharge as glacial streams, right? How do you put 30 times the volume of Lake Missoula on top of the ice sheet? Can you put it in the middle of the ice sheet somehow? You see,
if it's frozen.
This was the problem in why John Shaw's theory, even though you look at the drumlins, you study the drumlins, every single thing points to the same conclusion. They were formed by subglacial water flows. The problem is that the scale of the drumlin fields is so huge that it requires massive amounts of water. So the storage problem became the weak link in acceptance of John Shaw's work. Does that make sense?
Yeah.
Well, here's what I'm getting at. We don't need storage because we're talking about instantaneous catastrophic melting. There was no storage. It was instantly melted. Huge volumes of water gushed to the base of the ice sheet. The ice sheet is fractured into 1 million pieces, right? Huge volumes of ice directly sublimate into the vapor state and are spread around and then begin to rain out. Huge volumes of rain, which I think we can see the imprints of these incredible rainstorms in the southwestern deserts. I've looked at it in the Sonoran. I've looked at it in the Mojave. You can see it imprinted in the desert. You can see it imprinted in the Basin and Range province of Utah and Nevada, in these dry desert. You can see it in the Appalachian Mountains of the southeastern United States. I'm going to show you some evidence here in a second, so let's just keep moving.
Let's keep moving.
There are widely divergent theories on the formative processes of giant flutings and drumlins. Flutings are just like drumlins that have been, we saw pictures of them. I'll show you here. Let me go back. Okay, look up here. You see these long, skinny things?
Yeah.
Those are flutings.
Okay.
Divergent theories on the processes, for the formative processes of giant flutings and drumlins. Early work in Western North America invoked variations of direct ice erosion and or deposition as explanations. So the question is, how do you have a ice sheet grinding over the landscape, pulverizing the bedrock into thick layers of glacial till, and at the same time shaping that glacial till into these nice aerodynamic forms, streamlined forms? How does that happen? Well, this is why they've been arguing how the glaciers do that for 1.5 centuries. And nobody, there's different theories, different models come up. Here's maybe how the glaciers are doing it. Here comes John Shaw and says, well, it wasn't directly the glaciers. It was large volumes of water moving under the ice that did it. But then the people, the critics are going, yeah, well, if it's subglacial floods producing the drumlin swarms, these drumlin swarms are fantastically huge.
Yeah.
And it requires enormous volumes of meltwater, and you can't provide a source for that much meltwater, so get the hell out of here. That's pretty much. Yes.
Okay.
Numerous researchers continue to support these explanations despite recent work in northern Saskatchewan, Ontario, Quebec, and the Northwest Territories. This work has shown that enormous, turbulent, subglacial water flows better account for a variety of erosional bed forms, including giant flutings, ice cavity fill, depositional forms, and some types of drumlin. So here's near the headwaters of the Missouri River, and you see the modern river down here, but the channel, this is the channel that was cut by the water flows that deposited the erratics, the big rock.
Yeah.
This gives you a sense of the scale of the water flow right here.
Yeah. And
right? The modern Missouri River will never go out of this channel unless it gets deep enough to overflow the divide, which it probably will not anytime in the near future, because what's missing is 4 or 5 million cubic miles of ice immediately to the north, right? But yeah, this gives you a sense of the scale and so not far north of here is where the giant ripples were. So you can follow the train of the erratics, you got the ripples, and then you head into this giant valley, and it's captured what is now the modern Missouri River. And then, so this is mega-scale streamlined erosion, mid-continental North America. And you can really begin to see that you're looking at an erosion here that dwarfs Lake Superior. All of this is headed for the Gulf of Mexico. Here you can see what would have been streamlined islands within the flood flow. And if you look at these features here, just like what we were talking about in the scablands, the intermediate material has been removed. See, this, if this flow had continued, these islands would have been erased
away. Yeah.
Exactly. This was when I was shooting slide film, and then they had just installed the what do you call them, the security stuff in the airports.
You shot this?
Yeah, and well, what happened
was scanners, yeah.
The scanners fucked up my film.
Yeah.
Is what happened. So
looks like a animation or a video game, an old.
Yeah, I'd climbed up on this prominence, but we're looking out across a gigantic riverbed, a dry riverbed that reached from here. Like this would have been underwater. And you can't, let's see.
Are you standing on the top of the other peak?
I'm standing, I took this picture, so I'm standing above these guys looking out across this river, fossil river bottom.
Yeah.
But here's what you can, it doesn't show up here because the picture got screwed up. But yeah, you can see then from the air, this is what you got.
Yeah, wow. Giant ripples.
Aerial view of giant current ripples in the Mojave Desert near Cadiz dry lake bed. So again, this kind of stuff is all over and nobody has really paid any attention to it. Geologists generally aren't looking at surface stuff. They're not, most geologists are working in industry or for government, and their objectives are totally different.
Find oil.
They're prospecting for hydrocarbons, for precious metals. They're studying the water flow through the bedrock because they're wanting to know, the depth of aquifers, how much water might be available, all that kind of stuff. But it doesn't really lead into the question of, well, were these land features created catastrophically?
So most mainstream geologist work is about what can we extract from
pretty much
the earth.
And most of the geologists that are like doing this kind of work are doing it in their own time on their own dime. But hopefully
we can change that.
And this is, Scott, this is, okay, so this is 2009. So this is 16 years ago that I took this. I went out and traveled in this area. A couple of things that are interesting. You can see here, all of this in here, this is called bed forms. This is a result. You can actually trace. This was a huge water flow through here. Over here, you can see another. And then also look at this pyramid-shaped mountain. One of the things I like to point out is that both glaciers and water can create pyramidal mountains. So don't be too quick to look at something that's pyramidal in shape and assume that it's an artificial pyramid.
What was we looked at one of those in the glacier, where, what's the term for it?
The Nunatak or Nuna?
I think so. Nunatak.
Here you go. That's a beautiful example of an alluvial fan.
Yeah.
Can you see over there? So, a couple of things here. You can see the obvious connection between the fan splayed out and the channel. And the fan is built of material that was eroded in the downcutting of the gully. And so this is Mormon Point, Death Valley. And this would have been, certainly would have formed at the end of the last ice age. Now, in Death Valley, just like in Lake Bonneville, Death Valley had this giant temporary lake that filled it up. Lake Manly, it's called, and the water, again, about 1,000 feet deep. And if you look at this, you can see the high shoreline of Lake Manly right here. See that?
Yeah.
And then you can see successive shorelines as the water subsided and ultimately evaporated away. Because Death Valley has no outlet to the ocean. So any water that goes into Death Valley either accumulates or immediately evaporates away. So, for example, you see this gully cut here. So this gully came after the lake subsided, right? Because look, the gully cuts across the shoreline.
Mm-hmm.
You see that?
Yeah.
So that tells you relative timing. The shoreline was there first. When the water declined, then runoff from the hills up here could now carve this gully, and it it incised through the shorelines. Now look here, and you can see that the modern erosion and flow is building another alluvial fan, a small fan right there.
Oh, okay.
You can see that.
Yeah.
So you've got a scale invariant thing going on from this to this. However, this you can see that if this water level is up here, 1,000 feet deep, this is not cutting a gully. This can only downcut the gully once the water level's dropped. But again, scale invariance here. Look at this. As this fan is to this fan is to this entire deposit right here.
Oh.
Yeah. So now you have this massive flow of deposit into this basin while it's filling up with 1,000 feet of water rapidly, and then that water slowly evaporates away. When it evaporates away, it leaves a succession of shorelines, and now the post-deluge erosion begin, and so now you start, the more normal flows begin to cut and carve these gullies that transect the strand lines. And see, that's why they were so easy to downcut, because this is all just unconsolidated alluvium.
Mm-hmm.
Look at this, deeply trenched and eroded alluvial fans on the west base of Panamint Range, California. Note the remnant shorelines up here. So all of this, you begin to see here, when you begin to connect the dots. Yeah, that's when you begin to see the true scale of what we're talking about here. Then we have this. Origin of alluvial fans in White Mountains. Deposition by perennial streams on White Mountain alluvial fans appears to be of minor significance. Streams in the area appear to accomplish little erosional or depositional work during periods of normal discharge, either within the mountains or on the fans. Their theoretical capacity for load may be high, but the caliber of most of the available debris is such that they are incompetent to move it. In other words, the material composing this fan, the modern streams
Can't touch
aren't doing shit.
Yeah.
But then he goes on to say, a notable morphological characteristic of many of the White Mountain fans is the presence on their surfaces of large boulders far from canyon mouths. These are particularly conspicuous in the northern part of Upper Owens Valley. The largest boulder discovered is on the Marble Creek Fan. This massive granite block measures about 30 by 25 by 25 feet and has an estimated weight of 1,500 tons. The location of such huge blocks has stimulated much speculation about how they could have arrived at their present sites. And there's an example of one of those from an old journal article. That probably is this article here, 1963. So this guy is out there looking at this big old rock sitting on the surfaces of an alluvial fan going, how the hell did this get
here?
Yeah.
In 1963, too.
Yeah. What were you doing in 1963?
Those were the 60s. Crazy days.
Yeah, crazy days. Yeah, I was riding my bicycle all over the place and just about getting interested in.
I was more of a dancer
and an
artist.
Oh, you were a dancer. Alluvial fan, now get this, alluvial fans of the White Mountains, and by analogy, those of other Great Basin ranges, appear not to have been built by the ordinary processes of stream deposition. Instead, spectacular episodes of debris flow deposition have been irregularly interspersed with periods of quiescence. During intervals between major rubble flows, morphological changes on the fans have been minor. So again, back in 1963, this author, Charles Beatty, is constructing a model in his head of where you've got the normal, observed rate of change and not much is happening. Yet then that is interrupted by these, what he's calling spectacular episodes of debris flow deposition. Well, how do you have a spectacular episode like that? You have to have, here, you're looking at a you don't have the great ice sheets. Now you got some mountain glaciers, but I recently read that the contribution of mountain glaciers to the formation of Lake Bonneville was about 3.3%. So the vast volume, most of that volume of water was rainfall. That's what that tells us.
Yeah.
Yeah. And the same thing here. So here's my question. Now, these spectacular episodes of debris flow deposition, when these enormous rainstorms are falling over California, I would venture to speculate that that's happening. It's all happening at the same time. Yes.
Yeah.
In the Great Basin environment, the spectacular seems to have been the normal. For it is by spectacular processes that a large share of the grand work of gradation has been carried out. So this is Afton Canyon, a 150-meter deep canyon, that's almost 500 feet, that formed as a result of overflow and drainage of Lake Mannix, an approximately 215 square kilometer Lake Wisconsin pluvial lake in the central Mojave Desert. Stratigraphic and geomorphic evidence suggests that Afton Canyon was cut rapidly sometime after 14,230 plus or minus 1,325 years before present. The rapid draining of Lake Mannix and subsequent basin dissection have important implications for late Quaternary lake fluctuations in Death Valley. Well, let's see, if I put in, so this could have been as recent, based on this dating, if I put in 14,230 and I minus 1325, you'll notice how close that comes to the Younger Dryas.
Yes, 12,905.
Yeah, there we go. So two things. We have the sudden formation of this huge lake, Lake Mannix. It overflows. It then cuts a canyon 150 meters deep, which is nearly 500 feet. And it says then the canyon was cut rapidly, not something lasting hundreds of thousands of years or even tens of thousands of years, but rapidly. And it was associated with the rapid draining of Lake Mannix. So it appears that what we have is the rapid filling, the overflow, and then the rapid cutting of the canyon. And where was this water all ultimately headed? It was all going to Death Valley.
Mm-hmm.
So one year, Brad and I went and we followed this whole flow from the highest ancient lake bed we could find all the way to Death Valley. And all along that whole route, you could see the spectacular features of water, erosion, and deposition, water-carved landscape, where it is now extremely arid desert. So here, listen to this. Stratigraphic and geomorphic evidence suggests that the draining of Lake Mannix, the carving of Afton Canyon, and initial deposition in the downstream areas occurred rapidly. The conclusion that Afton Canyon was cut rapidly and that Lake Mannix quickly emptied has important implications for areas downstream of Afton Canyon. Much of the overflow must have passed all the way to Death Valley. And so here's the entrance as you go into Afton Canyon. You have mountains of alluvium, and you can see the hoodoos that are formed, which are very typical. What happens when you have these rapid depositions of large amounts of unconsolidated alluvium? They're going to be very subjective to post-depositional erosion, and that's what carves out the hoodoos and all the gullies and the sides. And here you can look at a section close-up of massive alluvial deposits at the entrance to Afton Canyon. We can see, here's a good example of scale, and then if you look at the structure of this, you'll see it's basically unconsolidated. There's cobbles, boulders, all kinds of things interspersed throughout. Why didn't a big boulder sink to the bottom? Well, the reason is because this material was extremely viscous when it was deposited. It was like a big, thick mud flow, essentially. And then by going into some of the 1 and 2 and 3 century old arroyos, you can see the desert floor, which again, if you look at this close up, I haven't put them in, but you can see suspended rocks, cobbles, and then in a lot of places you'll actually see boulders suspended. This is a mud flow. The whole desert floor is a dried out mud flow.
Mm-hmm.
Rio Grande. Let's see. And then Valles Calderas. This is quite an interesting place. Largest volcanic caldera in North America, 11 miles wide. And let's zoom in on this here. And there's a breach point right here.
Mm-hmm.
So this thing filled up with water. In fact, it's happened several times that water filled up and spilled over the rim. And this topo map, you can see these are subsequent volcanic eruptions that happened within the large caldera here. And then we're going to zoom in on this discharge point right here. So right here you've got what's called Battleship Rock. And you could say Battleship Rock, Valles Calderas. You find pictures of it. I've got pictures. So these blue lines represent the flow routes out of Valles Calderas. And so you had flows that came together right here and created the prow. It's called Battleship Rock because it looks like the prow of a ship.
Yeah.
Right? And when you go through the outlet channel, you start finding this kind of stuff revealed in road cuts and this kind of stuff.
So
Coarseness of boulder gravel is evidence of catastrophic flows. Degree of angularity suggests short transport from source or insulation of clasts, which are the rocks, by a surrounding finer-grained matrix. But these boulders here were most likely eroded through the cutting of the rim here and then dumped all down this trough. And then when you get down to the basin,
oh yeah,
you see the rolled boulders.
Mm-hmm.
The modern river, East Fork of the Jemez River, is not moving these rocks.
Yeah.
You look, here's Bradley. He's standing on an almost perfectly spherical 8-foot diameter boulder. So you know that this got transported a pretty good ways. How deep was the water have to be in order to carry this kind of sediment load? Look at the size of these rocks here. See?
That small river is not
even large. Look at these that are broken up and jumbled into creek troughs. This water here did not put those boulders there.
I don't think so.
And here's your Battleship Rock. And here's looking kind of up at the prow. That's it. So here's an example of a playa lake. The Wilcox Basin is a topographically and hydrologically closed basin in the northern portion of the semi-arid Sulphur Springs Valley in southeastern Arizona. In the past, the Wilcox Basin was intermittently occupied by larger and more permanent bodies of water. These lakes represent former stands of ancient Lake Cochise. As today, no external surface or subsurface sources of water entered the Wilcox Basin. Consequently, the large lakes formed whenever precipitation and surface runoff within the basin exceeded losses due to evaporation. A prominent shoreline representing a high stand of Lake Cochise circumscribes the basin at an altitude of 1,274 meters. So we went down there, explored the basin, found the shoreline. Let's see, do I have an additional source of atmospheric moisture that could have helped maintain a lake in the Wilcox Basin during the early Holocene may have come from, who would have thought, intense rainfall. Perhaps an intensified period of tropical storm activity provided supplementary moisture which maintained the high level of Lake Cochise during the early Holocene. With respect to the early Holocene high stand of Lake Cochise, one conclusion is clear. precipitation must have been greatly enhanced. Say, now we've gone from California, to New Mexico. Now we're southern Arizona.
Mhm.
We could go the whole desert region of the Southwest, right? Let's see here. When water filled the basin to an elevation slightly below the late Pleistocene maximum stand at 1,274 meters. In addition, the potential moisture from large tropical storms must also be considered in the hydrologic budget of Lake Cochise. Well, okay, so they're saying, looking for modern analogs, and the closest they can come up with is a huge tropical storm.
Yeah.
Okay, wait a minute. You had huge tropical storms over the deserts of Arizona? Well, yes, you did. But that just opens the door to trying to figure out what actually we're talking about. That doesn't solve anything. Now, when you go into the, let's see if I've got my, let me escape here. We're running out of time soon.
Yeah.
Just when it's starting to get interesting.
Yeah. So when you say tropical storm, I mean, coming from the evaporation of glaciers wouldn't be considered tropical, would it? Like if, let's just say something.
Well, yeah, I mean, so in other words, where are the biggest, most intense rainfalls on Earth?
The rainforest, yeah, yeah.
So what he's saying essentially is we're looking at something that's comparable to a tropical storm, that we would require that kind of rainfall. But for how long in order to fill this lake basin? I'm going to show you something here. I'm going to go zoom down here.
So he's just comparing them to tropical storms. I see.
Correct.
Yeah.
Correct. Yes.
That was the only thing he could come up with, where it's like, okay, well, there needs to be an immense amount of rainfall, and this is the only thing that I know
Yes.
produces that.
Okay, so right here, this is Wilcox Playa. This is where that lake was that it's being talked about here. These are the Chiricahua Mountains, right? So now the Chiricahua Mountains are rock that's formed, it's called welded tuffs, Tuff. It's spewed out during really huge volcanic eruptions, right? So all these mountains are built of this welded tuff. Well, welded tuff erodes very interestingly. And I'm going to show you a picture here. Now, we're going to see two things here. We're going to see a massive amount of erosion in the Chiricahua Mountains that would have had to flow off down into the lowlands. And we're going to see evidence of a massive lake in this basin adjacent to the mountains, right? So first thing we're going to do here is we'll go, and I'll show you some pictures that I took. Severely eroded volcanic tuff. Note the extinct lake bed. You can see the extinct lake bed right out here. That's Wilcox Playa. So a playa lake is an ephemeral lake. It's a basin where lakes can form, but they don't remain. They disappear. And typically your playa lake is going to be a very shallow. It's not going to be a large lake. But look at some of the, well, I should have had more pictures, but if you look up Chiricahua Mountains, you can see the spelling right here. I bet you'll find some really interesting, but you can see thousands and thousands of these pedestals.
Oh, yeah. Wow.
Yeah.
Wow.
Well, I was right. So what you have is you have evidence in these mountains of intense erosion. And then at the foot of the mountains, you have evidence for a gigantic extinct lake. I would argue that most likely those two events are related. The water that eroded these mountains created the lake that's no longer there.
Volcanic tuffs are made from volcanic ash, correct?
What is?
Tuffs?
Tuff, yeah.
Yeah,
Mhm.
tuff. Is there a volcano that?
Yes.
Okay. What is the volcano near this?
Oh, I don't remember. To be quite honest, I don't remember.
But that's not particularly significant for this story.
Well, the volcano would have been a number of million years ago.
Got it.
So it was different. So we're going to have to skip through some stuff if we're running out of time. This is the Hoodoos.
We got about 20 minutes.
20 minutes? Okay.
15,
Coal Mine
15,
Canyon.
20.
This is on the Hopi Reservation. Again, this is up on a mesa, and you can kind of see the rim of the mesa over here. And this is evidence of huge discharges off the surface of the mesa that have cut these channels. And you see the Hoodoos here?
Yeah.
That's typically something you'll see. And again, this is fairly soft material.
So just so I'm clear about the term hoodoo, a hoodoo is what is created once there's some type of deposit and it's or some type of alluvial deposit and it's still soft and it's easy to be eroded while it's soft.
Yes. And you see many, many hoodoos in Bryce Canyon is famous for its hoodoos. Canyon de Chelly, eastern Arizona, sheer vertical walls and freestanding pinnacle rocks are inconsistent with slow erosion. What's happening, see, is, let's see, I think we've got, here's Spider Rock in Canyon de Chelly. You'll see that this is a pinnacle rock, and it is being destroyed slowly. It's not being produced. You don't have features like this being created today that we can go out and point at and say, all we can do is assume it's, it's being created today by just wind eroding one grain of sand and maybe one drop of water at a time. So if I come back next year or 10 years from now or even 100 years from now, I won't see much difference unless, of course, what's happening here is mostly gravity is eating away. You might have, maybe every 10 years you might have a heavy rainstorm and a flash flood going through here, but they're not creating these pinnacle rocks. They're destroying them. Mm-hmm. See? Same way with arched bridges, as we'll see here. Let's see. Okay, so here you've got extinct cataracts and extreme erosion along Green River. This is in Utah. And once you've seen a recessional cataract, they're pretty obvious. But there's no water flowing here. So how did this landscape form? Well, are you saying that wind, if you're a gradualist geologist, are you going to say that wind has formed these? No, I would say, because if you try to say, well, they're wind, then what you're saying is, well, it's an ongoing process. It's just happening so slow that we don't really see change from year to year, decade to decade, except minimally, right? Well, on the other hand, maybe a better explanation is, no, these are fossil features in the landscape, and they're a result of processes orders of magnitude more energetic than what we see now prevailing in this landscape. Mm-hmm. And there we go. So here we've got buttes. So I'm asking this question: slow erosion over millions of years or catastrophic erosion? How has slow erosion removed the extraordinary amount of missing material? You can follow the strata here, and it has its counterpart over here and over here, showing that all of this intervening material has been removed. So, what is the assumption? My question is, okay, by what exact process was it removed? Does it make sense to say, wind did that? So the original landscape
blew all that away.
Blew it all away. Well, the original surface of the land was the tops of these buttes. All of this has been removed. Now, you got spire rocks like this, pinnacle rocks. Look, over here, these are called the thumbs, right? Because look, you see, you got the thumbs. Well, here's a question. Those pinnacle rocks are very fragile. What intensity of an earthquake would it require to just topple those skinny? Wouldn't take much. So the question is, when was the last time there was a seismic event in this area that would have been sufficient to topple those spires? And so if it was sufficient to topple those spires, then you have to assume that these rocks, the spires, are younger than the last time you had sufficient seismic activity that would have caused the collapse of those spires. Mm-hmm. And here is a Sentinel Mesa, 900 feet high, just over 1 mile in length. Compare with Steamboat Rock in Grand Coulee. Same height, same length, same size, This is sandstone. The other in Grand Coulee is basalt. But in terms of the morphology, they're almost, I mean, again, this is just about the same size as Grand Coulee. Look at here's your mesa, showing again what process removed all of this material surrounding this. Well, in the case of Steamboat Rock and Grand Coulee, everybody admits it was water, but nobody is going, well, this was water. It's because why? Because the implications of it are just too outside normal bounds of thinking. Sandstone arches. How do you get these? Aren't being created anywhere in the world today, except maybe on a minimal scale in where they found. Sometimes they're found temporarily, like if you have clay deposits next to a stream bed and you have a flash flood through there, you might come and find something like this. But you come back a week later, they're not there anymore.
Yeah, and you might find them in cenotes too, actually. Like when you're inside underwater in a cenote, you have small
there we go.
Small examples of this.
But take a look. What's this up here? I'll tell you what it is. It's a pothole.
Yeah.
It's been bored into the cliff face. Well, a pothole, what does that mean? That means you had turbulent waters up to this level. And I've pondered this for years, trying to think of any kind of uniformitarian way you could produce natural arches or rock bridges like this. And I finally realized, because I saw some new papers on the Missoula flood, and it was up on private property, so I've never been able to get up there to see it firsthand, but it was photographs of rock arches that were created by the same flows that created Grand Coulee.
Mm.
I said, well, there, we have an example. We have an example that nobody would dispute, that this rock arch, this rock bridge, was created by catastrophic flows that created Grand Coulee. Well, if that's the case, then how do you produce this? See, here's another example. These things are not forming. Show me anywhere in the world today where these are forming. So, anyhow, this even goes back to 1908. Some high-level terraces in southeastern Ohio. So about 30 years ago, so good Lord, what does that put us, 1878?
Yeah.
Professor J.J. Stevenson called attention to a considerable number of high-level terraces or benches occurring in the upper Ohio River region, almost absolutely level, ranging in height from 1,100 to 2,580 feet above sea level. These high-level terraces are recent, having been made since the latest warpings of the region and being very well preserved. Professor Stevenson explained that they are due to wave work on the valley walls and hillsides when the region was deeply submerged subsequent to the retreat of the ice sheet. So, on the walls of the Ohio River Valley, and what he's saying here is that they were deeply submerged. This would have been meltwater. Then this is from 1927. The outstanding topographic feature of northern Indiana is the Great Till Plain, beneath which is buried an ancient pre-glacial erosion surface. Crossing this broad till plain in a generally western direction is the Wabash Valley with its major stream valleys, beneath which is buried. So what you've got is thousands and thousands of square miles that has been eroded, and other thousands and thousands of square miles that has been buried.
Mm.
Now, when you take account of the massive degree of geomorphic work that has occurred during, say, between 8,000 and 14 or 15,000 years ago, for the archaeologists to think they've got it all figured out and that they know what's buried under hundreds and hundreds of feet of, great masses of glacial till, that they knew what was in some valley before hundreds of feet of bedrock were originally ripped out. No, they just don't know. They don't know. But they think they do. The Wabash Valley is a great sluiceway, which came into existence during the Pleistocene glaciation by the erosive work of debris-laden floodwaters which debouched, there's a French word for you, from the melting glacier. Not only the Wabash, but the Salmone, Mississinewa, Eel, and Little rivers are superimposed streams which have cut down into and in some cases through the drift from 50 to 100 feet below the upland till plain. So in other words, there's a buried land surface and it's under 50 to 100 feet of glacial till.
Mm-hmm.
Now, are you going to tell me, if you're an archaeologist, that you've investigated all that and you know what you're going to... No, you're not.
Well, they might.
Well, they will claim that.
Yeah.
Yeah. Thus, in northern Indiana today, we find set into the till plain a glacial sluiceway which was once filled with a great rushing torrent of debris-laden waters, but which is now occupied by a rather insignificant stream that covers but a fractional part of the floodplain of its mighty progenitor. So, I mean, see, we can keep going.
Underfed rivers.
Yes, on and on. Bluffs overlooking the Mississippi River along the Wisconsin-Minnesota border. Okay, so I'm standing, this picture, I don't think I took this picture, but I've stood on this point, and we're up on a bluff here that has its counterpart on the other side.
And how far away is that?
Oh, that's got to be like 3 miles, 2.5, 3 miles.
Okay, I've learned a lot of terms today, but we've looked at an immense amount of land being removed in all different parts of the United States. We looked at some depositional structures as well, but it seems like this is a lot of land that has been removed.
Oh, yeah, absolutely. Absolutely, it's a lot of land that's been removed.
Where do we find more of this? Or maybe I'm just not understanding, but we've looked at some depositional structures. We were talking about this at the beginning of last week with the Nile River Valley, where there's essentially 8,000 feet of sediment that fills up these. Where do we find more of this land through the landscape of North America?
Oh, pretty much everywhere. I mean, yeah, almost everywhere. I mean, that's the thing. Once you begin to realize the scale and scope of the geomorphic work that has transpired since the last ice age, there's almost no place on Earth that's been untouched. I mean, that's just the way it's revealing itself. So that's the thing, is that I would like to take these archaeologists and send them off for about a year study in catastrophist geology. Then they maybe would not be quite so certain that they have it all figured out what was going on 20,000 or 30,000 years ago in terms of human civilizations or what kind of societies we might have been building or engaged in what may have evolved in terms of, human societies or whatever. And they're not, I mean, they've already decided that there was no such thing. And so, therefore, they've sort of necessarily blinded themselves to the evidence that you might find. Think about out there at the Savannah River at the site, Dr. Al Goodyear. He's told the story. And I find that story really sort of encapsulates the whole problem here. He was excavating down there down near there. It's off the Savannah River. I forget the name of the Topper site. He was down there excavating the Topper site. And, he went down. We were there. I went there with George Howard and Graham Hancock and Chris, who's kind of leading some of the studies of the Carolina Bays now.
Cottrell.
Not Chris Cottrell. Chris, he's in the Comet Research Group. He's co-authored or been lead author on several of the major papers that have come out in the last few years on...
Dr. Moore?
Dr. Moore, of course, Chris Moore. Yeah, that's what I'm talking about. So he was there. Anyways, we went with Dr. Al Goodyear. We went to the museum first. He was showing us the artifacts that he was finding at the Topper site. We went down to the Topper site. he showed us where, I think, 6 feet or so below the surface where the younger Dryas boundary horizon was from, a little bit less than 12,000 years ago. Well, and then he was telling the story about how people kept asking, well, what's lower down? And his response was generally, well, nothing. I mean, because we know the Clovis were here first. So we're not going to find artifacts of human occupation of this site earlier than the Clovis, because that's the standard model. Everybody accepts it. Clovis first, right? Well, then, Dr. Goodyear's obviously an open-minded person who was willing to think outside the box a bit, because he decided, after enough apparent pressure from students and others, I guess, whether there was anything lower, he decided to excavate lower. And he went down, and what did he find? He found another cultural layer, considerably lower. Mm-hmm. And I think it dated to about 30,000 years ago.
Think about that, yeah.
And so that completely didn't fit the prevailing model, so his work has been ignored, conveniently. But see, that to me represents, okay, so the assumption was, well, there's nothing there, so why look? And then you look, and there's something there. Well, I think that's a widespread problem across the whole spectrum of archaeological research, is too many assumptions about what may or may not have possibly happened in prehistory. And if you would go, well, maybe we just need to go look. But again, the problem is that this lack of understanding of the intensity and severity and magnitude of these geomorphic processes and how they can instantaneously completely alter a landscape. So whatever would have been there gets lost in that process, right? So that's the problem. So we need to be able to find, first of all, be more open-minded to the possibilities of what may or may not have happened 15, 20, 30,000 years ago or even longer. And then, actually look. But the challenge will be knowing where to look. Because, are you going to excavate through 200 feet of a thick boulder bar to see what's sitting on the bottom of it? And even if you did, the processes that deposited that boulder bar or that debris fan or whatever probably also erased whatever was there.
Uh-huh.
So there's the problem. And we've got a lot more to get into here to try to educate people about this. It's a whole language. If we're going to come to a working, functional understanding of this language, yeah, it's doing what we're doing is the way to do it. We're investing in time. We're learning the terminology. We're going through some of the scientific work in the papers. We're looking at the images. In the next one, let's just try to look at some drone footage.
Let's do it.
And
maybe some LiDAR scans.
LiDAR scan. Well, yeah, we didn't get that far. If we had another hour, we would be getting into LiDAR scans that are coming up here. Here's a LiDAR scan of the Minnesota River Valley. And you can see this little ribbon here. That's the modern river. And here's the ancient channel. Beautiful example of an underfit river. And I was standing right here next to this gully, or was it this one, looking into this thing, and that's when it began to dawn in my mind that something had gone on there, something had happened. Because I could, standing right here, I could look and I could see this, and then I could see this, and something didn't seem to add up.
It just didn't fit.
That was 1969.
Wow.
Summer of 69. That's really kind of where it, yeah.
Wow, this started in the 60s for you.
Well, yeah, 69.
We've been here for 3 days having a lot of fun. So we've covered a lot of stuff, and this is always super interesting. And
oh, yeah.
Thank you, Randall.
Oh, you're welcome. I've enjoyed it.